No, it's out of 20.
Mine's out of 25.
Is it?
Yeah.
Oh, that's a great book, right?
Yeah, I don't. Lots of that work.
Oh, well, I don't know if you put it down.
Oh,
That's the same.
yeah, I think so.
No, I must have done it. I'll fix it. I'll fix it. It should be out of 20. There were 4 problems. It should be out of 20. How are we doing today?
Good.
Good. So remember, we're going to have a test on Thursday. So we'll chat about that during the. I'll do another example or two with extrapolation. And then we'll talk about what's on the exam. Next week, I'll assign your first major assessment. That'll kind of put together a bunch of ideas outside of class. Hello, how are you? Good. We'll talk about that on Tuesday. Thursday, we won't have class because I'm going to a conference, so I won't be here. So we won't have class next Thursday. So you'll have that opportunity to work on your major assessment. So you'll have at least an hour and 15 minutes for you to be able to work on it. So, in any event, any questions at all before we dive back into things? Things are good? No. Okay. Good question, though. But no. All right. So we talked about extrapolation last time. So remember that our guiding principle for creating new estimates. So we had that quantity Q that we were approximating. We were using that formula that looked like your new estimate, which we used basically half of the previous, the H value, whatever we were plugging in. And then that was going to be plus 1 over 2 to the n minus 1 times f of h over 2 minus f of h. We also wrote that out in words, right? So the f of h over 2 part is your next approximation, supposedly the better estimate based on the h value, making it half the size of what it was before. The n here says that your original approximation, your f of h, was your order n approximation. So that's what's going on in the exponent up here. And then you're doing the new estimate minus the old. The important thing is to know that this exponent that you're using up here really is your order of the approximation. And the idea is that if you do this extrapolation process, you get a new approximation. So this is a new formula to approximate the quantity that you're trying to get at. And its order is at least n plus 1. So it gets better. Sometimes it's even better than that. We've seen other approximations where the odd terms cancel out, for example. So it goes up by 2. All right. So that was the formula we talked about last time. We did one example in Excel. So let's see if we can do another one here to make sure that we're all on the same page. So keyboard connected again. All right, so let's just use our forward difference formula to approximate the derivative for a function. So let's say we use the function, doesn't matter. Let's say we did e to the cosine of x. Oh, hey, that's ugly looking. And let's say we want to approximate let's do f prime of 1 using extrapolation. All right, so we've got a couple of different formulas that we've used to approximate derivatives. We'll talk about how we can derive some other ones today as well. Maybe for the first derivative, maybe for the second derivative, just talk about how we can derive them generally speaking. like I said in this one, let's do the forward difference. Remember, your forward difference is just a fancy name for what you learned back in Calc 1, right? So your forward difference formula is the f of x plus h minus f of x all over h, right? And remember, this is order 1 approximation. Okay. We had the other ones as well. Remember, we had the backward, this is the forward difference. We also had backward difference approximation, where you did f of x minus h. That would be the backward difference. It also has order 1 as well. We also had the central difference, where we did f of x plus h, f of x minus h over 2h, and that had order 2. That was a better approximation if you're trying to do first derivatives based on the error curve. All right, so let's see if we can set things up here. Also talk about how we would do it by hand if we were going to do a couple of steps in there, because again, your exam, I'm going to expect you to do these things on your calculator, but not long, okay? All right, so remember, we're going to make our h be small. So let's just say we start off with maybe 0.1, and then we'll divide it in half each time. So I'll take that divided by 2, and let's just copy this down a couple of spots. You know what I'm going to do? Never mind. I'm going to insert a row here so I can put the orders across the top. Only because I'm going to use the numbers up here at the top so I can refer to them rather than type them in each time. Okay. All right. So our order 1 approximation literally is just plugging these things in to our approximation formula that we have. Okay. So across the top here, I'm going to label what the orders are. So I'll make 1. When we do Richardson's extrapolation one time, the next one should be 2. Next one should be 3, right? As we go across. Okay. All right. For your first column here, we're literally just going to plug in x plus h and x over h. Our x value is 1, and those are the h values on the right. Okay. So in the first one here, we'll put in, we have e to the cosine of, what goes on the inside here? 1 plus the 0.1, because it's x plus h, right? So we should have, remember again, on Excel and in R, we use exp for the e to the power, right? So it's exp of cosine of 1 plus a2 here. What should go next? Yeah, just the x, and the x value in this case is just 1. Also need to sure we keep track of all of our parentheses here. Need parentheses around my input for the cosine, parentheses around the input for the exponentials, and then I need parentheses around the whole numerator. What do we divide by? Divide the h, the a2 there. Good. Having you do this on an exam, I won't have a really complicated function, so you'll be typing things in your calculator. Process is the more important thing. But again, that first step that you're going to do for your h values that you have, you're going to just plug those in to the approximation that you're asked to plug it into. In this case, I said let's do it for the forward difference, so we're plugging it into this approximation that we have. So far, so good? Okay. So if we do the next one, or actually, if I hit enter, all I should have to do is pull this down, right? Okay. Now we can use the extrapolation formula here and use the fact that I've typed the orders at the top to help us out. Okay. So, pardon me. Remember that our extrapolation formula, if I write it out in words, will be the new estimate plus 1 over 2 to the n minus 1 times the new minus the old, right? Okay. So in this one, the new estimate is the one that's right next door, right? That's the one where we have the value. So B3 plus 1 over the denominator here should be 2 to the order of the previous approximation, and this is why I typed the numbers in at the top. The order of the previous approximation should be this 1 here, right? Right? So I want to refer to B1, but when I copy this, I don't want the row to change, right? Because I want to copy it down. Now I do want the row to change, or the column to change as I copy it across, because I want to refer to the orders in each column. So I want a $sign next to the 1. So when I copy it across, it'll change the column letter, but when I copy it down, it won't change the row. So I'll still be referring to the same row, but when we copy across, it'll change the order appropriately as we go across. And then minus 1 here, and then multiply by the new estimate minus the old estimate. So the B3 minus the B2. And then again, on your calculator here, of course, if you were typing this on your calculator, you wouldn't even bother typing in this piece because this is going to simplify to 1 your first go around, right? So you would just do, if you have an order 1 approximation, these next values are just 2 times that one minus that one. So if you're typing in your calculator, you can do it a little bit more quickly. Now we can now we're all set up to copy and paste, right? Okay, so these were our order 1 approximations. Here's our order 2 approximations. If I just take these two and copy it over 1 more, that's order 3. And then if I just take this one and copy it over 1 spot, I now have an order 4 approximation here. I'll just label it. It's not doing anything for the next one. If you wanted to get an order 5 approximation now, what would we need to do? Good. Yeah, I have to drag all of these down 1 row. I need 1 more row to do, right? So you need to drag this row down 1 and copy 1 spot over, and then you'd have an order 5 approximation here.
Can you click on the C3 box?
Sure. You got a parenthesis off somewhere?
Yeah.
Yeah, okay. Yes. You have a mid parenthesis in the wrong spot. We've got to close that off. So I have e to the cosine of x plus a. So we've probably got another extra parenthesis somewhere. Let's see. Yeah, sure. Oh. Nope. All right, let's see what's going on. Oh, there's an extra parenthesis in here. There you go. Gotta watch those parentheses.
Yeah.
All right. Everybody else okay getting those in there?
I'm not getting the right numbers on the D column.
You got.
The one
Oh, hey, it went away. That was fun. Let's see what we got. Oh, that's right. One, that's right. That's super weird. Why is that different? One. Oh, I see it. Your minus one needs to be outside of the exponent. You've got parentheses around the exponent there. You don't let parentheses around your exponent. Oh. That's what's causing it. It's just off by enough. Yeah, so you had parentheses around this whole thing right here. You don't want that in there. Everybody else okay? So one of the ways we could verify that this really is of the orders that we're saying they are is that remember that the error should be a constant times whatever the h value is for that first approximation. It should be a constant times whatever the h squared is times the second approximation and so on down the line, right? So if we were looking at these, well, we can do the derivative of this. Your derivative would be negative sine x times e to the cosine x. Right? I must have deleted something. That was weird. Oh, it's because I'm... Oh, for heaven's sake. That's not what I wanted to do. Do it this way. There we go. I bumped it with my hand. Times e to the cosine x. So your f prime of 1 would be negative sine of 1 e to the cosine 1. Right? So if I go over here and look at, here's your estimated value. The true value should be what I get when I plug in 1 into this, right? So here's your estimated value minus, or I guess it'll be plus because it's a negative sign, times e to the cosine of 1. And then divide by the h value. Again, each of those things in the first column should be an order 1 approximation, right? So if I put this in, so I've just done the error. So I did the estimate minus what the true value is, and then divide by the h. I should see a constant or something close to a constant all the way down, right? So I put this in and pull roughly the same value. Bless you. Roughly the same values, even a little bit better, right? They're going down each time, right? The idea here is that it should be on the order of h, which is not going haywire, right? The constants may change depending on the value, because remember when we're doing those, when we're saying it's on the order of a particular one, we're assuming on a constant times something, but really what we have is that with Taylor's theorem, you got the derivative at some point in between, and that point that you're using at the derivative might change depending on where you are. But it's fairly close. It should be on the order of h, which it is. It's not bad, right? Nothing's going crazy there. And then you should see something similar if you did the exact same computation in the next one. Except do h squared rather than the h. That's okay? Okay. We could do other approximations. We've done it with derivatives. And like I said, we do it with derivatives because you're used to estimating derivatives in calculus. It's one of the first things that you do in calculus is estimate derivatives. But this formula, this extrapolation formula, will work for any approximation thing that you have. Okay? So it'll work for, remember doing those approximate integrals ideas back in Calc 2. It would work on those formulas. It'll work on any of the formulas that you're interested in trying to get it to work for. Okay? If you have an approximation formula and you know what its error order is, you can get better approximations with better error estimates just by doing this extrapolation process, which is nice. Anyway, besides this last column here, any questions on how we're getting these? Let's talk a little bit about how you can create some of these and check their error estimates. So let's do another example here. Back over here. So let's say you were asked to develop a first order approximation of the second derivative using f of x minus h, f of x, and f of x plus 3h. Why those in particular? Who knows? But the process is the same no matter what you're asked to use. At least the process that we're going to use is the same no matter what you're asked to use. Okay. So again, all of these that we're going to do, we're going to start with using looking at the Taylor series expansion for the function at f of x plus h. So they're all going to look the same as far as that goes. So remember that your f of x plus h expansion will look like f of x plus f prime of x times h plus f double prime of x times h squared over 2 f triple prime of x times h squared over, or h cubed over 6. Next one would be the fourth derivative times h to the fourth over 24. Where are the 2, 6, and 24 coming from? The factorials, right? So remember your denominators here are your factorials of whatever derivative you've taken, right? We're assuming that we've got the Taylor expansion around the point x, and we're putting in x plus h. And you put in x plus h and then minus the x, that's why you're left with an h left over. All right. And then, of course, this process continues. Depending on what order error estimate you're trying to find, this process would continue. All right. So every one of these problems that we're going to do is going to start with this Taylor series. Okay? This particular problem is asking you to develop a first order approximation in terms of these three things. Let's look at the x minus h and the x plus 3h first. If this is my expansion when I've got x plus h, how am I going to get an expansion for x minus h? What are we going to do? Yeah, so we'll just replace the h with the negative h and put it in, right? The effect of that is like what Austin's saying, it's going to flip-flop your negatives for all the odd powers of h, right? So your f of x minus h will be a minus f prime of x times h, still plus for the second derivative. It'll be a minus the third derivative. Oops. It'll be a plus for the fourth derivative. And the next one, I guess, will be a minus. So I should probably put a minus there. So we're using the Taylor series expansion for f of x plus h, and just replacing the h with minus h, you get that Taylor series expansion for the x minus h. Probably want to do the same thing for your x plus 3h, right? So we can actually change something here, right? What's it going to look like if I do x plus 3h? What's going to change? Yeah, this will be multiplied by 3. This one will get multiplied by 9. This will be multiplied by 27, 81, and so on down the line, right? You're going to replace h with 3h, and then you'll have those powers of 3 that will come out. All right, so this will be f of x plus 3 f prime of x times h plus 9 f double prime of x times h squared over 2. This will be 27 f double prime of x, or f triple prime of x, sorry, times h cubed over 6. And I forgot my 81. Not worrying about simplifying the fractions right now. If we need to, we'll do that at the end. Are we okay with those Taylor expansions? That's just composition of functions, right? Changing out the h and putting in something else different for it. Okay. This particular problem asks you to get a first order approximation of the second derivative. And it says using only the function values at those points. By the way, that's the whole point of this entire process, is that we're trying to get approximations for derivatives only in terms of the original function. Okay? The reason why, if we think about it from an accuracy standpoint, if I only have the values for the function given to me, I can approximate the first derivative, but then I'm using approximations of the first derivative to try to approximate the second derivative. There's going to be error compounding there, right? If we can do this by just using the exact values that we know, then that'll minimize those errors going through, right? One of the things that you're hopefully have been taught at some point is, as you're going through a problem, it's best not to round as you go through, right? Because if you round, then you compound rounding errors, right? Leave all the digits in your calculator until the very end, kind of thing. Same concept here. All right. The reason why I mention that is, if I want to only use these three things to approximate my second derivative, what better happened with the first derivative? It needs to go away, right? So can you look at these two expansions and figure out what you need to do to them to make the derivative go away? Yeah, multiply this by 3 and add down, right? Okay. So when we do that, if I do 3 times f of x minus h, and then add, f of x plus 3h, we'll get 4 f of x, right? Yeah? Okay. Over here, when I multiply this one by 3, I get 3 halves plus 9 halves. That gives me 6. So I get 6 times f double prime of x times h squared. Here we have negative 3/6 plus 27/6. That gives you 24/6 or 6, right? The next one, I'd have 3/24. I mean, this constant is not going to matter at the end, but we'd have 3/24 plus 81/24. That gives me, what, 84 over 24? That's divisible by 3. Yeah? So you get 20, whatever that is. 28 over, I guess it's divisible more than 3. It's divisible by 6. So you get 14 over, oh, I guess it's divisible by 12. If I could do that. How about 7 halves? 7 halves, fourth derivative of x, times h to the 4th. And then so keep going. That constant is not going to matter. I could have just left it as 84 over 24 and not try to reduce the fraction in my head. Yes, thank you.
Would the third derivative constant be 4?
Oh, it's 24 over 6. Thank you. Yep. That's what I get for doing arithmetic in my head. That should be a 4. Good news is I don't really care about that particular constant, but yes, you're right. Are we okay with that so far? Do we know why we did it? That's more important. I wanted an approximation for the second derivative only involving the original function, right? So I wanted the derivative to go away. I wanted the first derivative to go away. Yeah, lady.
This might be a bad question, but why are we not using just the regular f of x? Like, why are we only using the f of x minus h and the f of x plus 3h?
Well, if I put the original f of x in there, I don't have anything to get rid of this so far.
Okay.
I right now I was just trying to concentrate on getting rid of that.
Okay.
Yeah, we're gonna the f of x piece was gonna come here in a second.
Okay.
Yeah. If I try to put the f of x in here, there's nothing. F of x just is f of x at that point, right? I don't have anything to cancel this off. I had to use these two things to get rid of the derivative.
Okay.
Yeah. All right. Here's where the f of x part's going to come in. We're trying to find an approximation for the second derivative, right? I want to try to solve, well, not really solve. This part's going to be your error term, right? Okay. So if I ignore the error and solve for the second derivative, what do I need to do? Subtract your 4 f of x across and then
Divide by 6h squared.
good, exactly. So if we solve for this piece, that's where your f of x is going to come in when I subtract. So we'll have the second derivative at x will be this, I'll write it this way, f of x plus 3h minus 4f of x plus 3f of x minus h all over 6h squared. And then there is an error term on the end, right? All the signs would flip when I move it to the other side, but I'm not too worried about the signs. What is your error term going to be in terms of? Well, remember, to solve for f double prime, we're dividing by h squared, right? So this first power here is going to be just h to the first, right? This will be h squared and so on down the line. So the error will be in terms of what? Yeah, first order. Good. So that'll be O of h. What's that? Oh, remember on the order of, we don't care about the constant. It's the power of h that we're interested in. Because on the order of means that we're doing some constant times that thing. So the 6 doesn't matter as far as that goes. Yes, we would need to divide everything by 6 there, but again, it's just some constant.
You don't care about the constant, you want to get the constant in there on the most part back here.
Here?
Do we
I cared about it here, so I'm going to make sure I keep track of it here. But you're right. These other ones, I could have just put some constant. I don't care. Yeah. If you know that this is where you want to get to, and you just want to label these as letters, that's fine.
And also, if you want to do up to third derivative, then you care about the third derivative and the. Okay.
Yep, exactly. That's exactly right. Yep. So now we've got first order approximation only in terms of those 3 function values. But again, the reason why I wasn't worried about f of x to start with was because I needed to get rid of the derivative, and f of x doesn't help me get rid of the derivative. But notice it came up when we solved for it. Where it popped in. Should we do another one? Yes. Let's say we want to do one for the third derivative. Why not? Let's do one with the first derivative, see what happens. All right, let's do one. Well, that was second. Let's do one with the first derivative. Let's say you want to develop a second order method for the first derivative using f of x minus 2h, f of x, and f of x plus 3h. So again, what do we start with? Again, your Taylor series, right? Probably just as easy to write out what f of x plus h looks like to start with. So far, so good? I thought you guys rewriting the same first step as I wrote in the previous problem. All right. As far as the let's think about what needs to happen as we go through this. By the way, if we're going to get a second order method, let's think about what we're solving for. I want to get an approximation for f prime, right? I want to get an approximation for f prime. So when I divide through by h to solve for x, well, at some point I'm going to solve for f prime, and I divide by that h, right? If I divide by that h, that only changes this to a first power, right? To get a second order approximation, that means eventually what's going to happen to this term? It's got to go away, right? I need to make this term go away in my approximation to get a second order approximation, right? Because if there's an f double prime of x in here, it's going to be attached to an h squared, right? When I divide by h, it's going to be an h to the first power, unless the constant is 0 that's out in front. So our goal in this case, to get a second order approximation for this, is I got to make this thing go away. Okay? So let's do that. Again, the f of x piece we'll use later. Let's use the two pieces that we can actually plug something in for h. Have f of x minus 2h. What's that going to look like? Yeah, good. So the signs will alternate, right? Because we're putting a negative in. And then we'll also get what? It'd be powers of 2, right? So the next one will be a 4. The next one will be an 8. And it'll be a minus. Oops, forgot to alternate my sign. And so on down the line. It'll alternate in sign because of the minus sign. The powers of 2 come from the fact that we're putting a 2 in with the 8. All right? We're going to do each of those powers. Likewise, when we put the x plus 3h, the signs will alternate, but what will come out in front? Powers of 3. Good. So far, so good? Yeah? All right. Again, we said we want to get a second. The reason why we're going to do the next step is because of what we're trying to get to. We want a second order method for the first derivative. Again, if I'm going to solve no matter how I do a combination of these things, if I'm going to solve for the first derivative, I got to divide by the h. If this term is still here, I'll have a second derivative times an h on an h squared, right? Right? So I need this piece to go away. So the next step is completely motivated by the fact that I want this one to go away. Right? Let's ignore everything here. I need to make the 4 and the 9 go away. What do I need to do to each of these to make the 4 and the 9 go away? So I probably need to get some sort of like a least common multiple idea, right? Make them both the same. Let's at least common multiple of 4 and 9. 36. So you multiply this one by a 4, and this one by a 6, and or 9, right again. This one by a 4, this one by a 9, and subtract them. All right? Agree? Okay. All right. So I'll do 4 times the second one and 9 times the first one and subtract it off that way. So I'll do 4 times the second minus 9 times the first. What's your coefficient on the f of x? -5. Good. The coefficient on the derivative part? The f double prime part goes away, doesn't it? It was the whole goal of this. And this is what Matt asked me just a little bit ago. Do I care what the constant is on the next one? Well, it needed to be a constant times it, right? But all I care about is that it really is a constant, right? Because that's going to be this is going to be the first term in your error term, right? So all I really care about is that it's some constant times, oh, I'll write it as h cubed. I don't even need to worry about the derivative part, right? I want it some constant times h cubed, right? That's the whole point. I don't really care what the constant is. You can figure out what it is. I think Austin was typing it in as I was talking about that. What did you get for that one? 30. You also get 30 for this one. Okay. But again, I don't care what it is. I just care that it's a constant. Right? That's all we care about. Because again, we're talking about the x being fixed. So I have a 30 and then a fixed x. Right? So I just have a constant out in front. So now what do we get when we solve for the derivative?
F 4 x plus 3h minus 9 x minus 2h plus 5 f of x.
Yeah, I'm just put it in the middle because it's just for aesthetic reasons, but you're exactly right.
And then all of that over 30h.
Good. And then on the end, we'll have O of h squared. Good. I'm not worried about this part in my solving until what I'm writing down the error term for, right? I need to add the 5f of x to the other side and divide by 30h. When I divide by the h in particular, the power on this one's going to be an h squared, and the rest of your h's will be bigger powers. So this will be second order. Does that make sense? Notice we're basing all of these off the Taylor series. We're hand waving a little bit. Really what we're doing here is saying that this entire error part here can be gathered into one term from Taylor's theorem, right? And then we have a constant in there. And then we're really hand waving a little bit because depending on if I move my x around a little bit, or my h around, I guess I should say technically, if I move the h around a little bit, that piece that we use for the derivative, you might change the input. So what we're really assuming with these functions is that we have nice functions that small little changes in the h isn't going to change your derivative by much. Okay. In particular, you hope your function is differentiable all the time. So this is, to give you an example of what bad might happen, if you try to do this for maybe the square root function around 0, you know that you can't differentiate around 0 very easily. In fact, it's not even defined on the left side of 0, right? Okay, so you'd have issues there because again, that derivative keeps getting bigger and bigger the more derivatives you take when it gets close to 0. If you're near spots where it's not differentiable, or if you're near an endpoint, what we're saying here for the error term may not work. It probably won't work. Generally speaking, from a numeric process, boundaries suck. Anything that's close to a boundary, and by boundary it may mean a bad derivative, it may mean a discontinuity. Working around the boundaries is hard. Just as an example, anytime you've got anything that's going to be a particular stress point, it's always you're going to have to worry about what happens if it gets close to a corner. Because corners are just bad in general, and they're hard to approximate. I mean, honestly, a lot of the numeric methods that people work on is trying to work around what happens on boundaries, because they're hard problems. If you've done anything with, I can't remember the term for it now off the top of my head. If you've done anything with chemistry and you pour something into say a graduated cylinder type of thing, you'll notice that it'll stick up on the ends a little bit. Right? The liquid is fine in the middle. That's easy. But then trying to approximate what happens on the end with the liquid, it's hard because it's starting to stick and it's bending and all that stuff. Right? So you get those kind of issues there on the boundaries. Just generally speaking, from an applied mathematics perspective, boundaries suck. They're hard to deal with. They require special methods to get at it. There's things in differential equations called boundary value problems, where you're trying to what happens at the boundaries. We're in the next stuff that we talk about with doing some some interpolation of points. We're going to be trying to work on what happens with the boundaries and handling them in different ways, depending on scenarios. Anyway, questions on that one at all? The main reason why I went on that little bit of a diatribe there is that we are waving our hands a little bit here when we say this. It works nicely if your functions are nice. If your functions aren't nice, near where you're trying to find the approximations to your derivatives, our argument doesn't work anymore. That's more of a question for a more advanced class than what we're doing. All right. Any other questions on that at all? Again, this is the main technique of doing this. Get your start with your Taylor series approximation. We're trying to solve for the first derivative, right? That was what we said we needed to do. And I needed to make this thing go away. That's what motivated us through the entire problem, right? Same idea up here. Going all the way back up here. We were trying to get a method for the second derivative, so I needed to make the first derivative go away. We were motivated entirely by that. And then just did an error analysis on the end. Are we okay with the numeric idea, though, of getting those approximations? Being able to do those next approximations like we did with the Richardson's extrapolation in Excel? I think you can reproduce it with a calculator. For a few steps. Again, things I'm going to ask you on the exam are going to be a few steps on the calculator. Just make sure that you understand how the algorithm works. Talk about the exam a little bit. Okay. So, things we've done. We talked about machine representation in numbers, right? We'll write things down here. So, a couple of problems that I could ask you about. Literally, one would be change a number to machine representation using single precision. Right, we did ones like that on homework. Okay. Other type would be largest and smallest possible numbers. So again, if I give you a certain number of bits for the exponent and a certain number of bits for the mantissa, what's the largest and smallest number that we can represent? And ones I do on homework as well. We also talked about equation solving or root finding methods. One method that we used was bisection method. How did bisection method work again?
So, it wants to do two things.
And then
You dropped off. One of the,
dropped off one of them. How did we drop off one of them? What did we look? What did we do, analyze next after you found it bounds?
oh, you did the midpoint.
Did the mid-
Found which one. What?
Yeah, exactly right. So you first find 2 points in between where it crosses, right? Look at the midpoint, and then between either the left endpoint and the midpoint, or the midpoint and the right endpoint, did it cross? Replace the one you don't need anymore, and keep doing that and having the interval each time, right? Okay. For a bisection method problem on the exam, I will give you the 2 places to start so that we're not all starting in different places, because otherwise it's a pain in the rear end for me to possibly get 19 different starting points. Okay. So I'll give you the 2 numbers to start with, so you'll know that it's in between those 2 values. Okay. And then go from there. Again, I'm looking for like 3 steps. Make sure that you know how to do it. Okay. Understand the process. We also did Newton's method, right? Okay, oops, let's do the capitalizing. What did we have to do for Newton's method? Yeah, so what was the formula for? Mainly the formula was what? How soon we forget.
X minus the function value divided by the derivative value.
Good, yep. So you start with an initial guess, and then you get new guesses based on old ones by looking at where the tangent line crossed the x-axis. All right. So you have some initial guess, whatever that initial guess happens to be, right? What don't we want the initial guess close to? Yeah, horizontal, right? That can throw your root finding off way away, right? We don't want that close to a horizontal. Mainly because why? What are you dividing by here in the next step? You're dividing by the derivative, right? So if you're close to a horizontal tangent, this will make your fraction blow up, which is bad. The idea behind Newton's method, again, is that tangent lines are good approximations to functions when you're close by the point of tangency. So if you're close to a root, your tangent line root should be close to your function root. You should be a little bit closer, then do the same thing, find the tangent line at that point, and you should be honing in on where you want to go. Again, I'm looking at like 3 steps. Okay? Not anything that's a big deal kind of idea, right? Pardon me. We also did secant method. I don't know, matter of remembering the formula, right? Remember what the formula was for that one? So you said this way? Oops. Yep. Times the function at where? X min? Say that again? Oh, X min minus that whole thing. Sorry. Oops. Thanks. Oop. Like that. If I can write it correctly. Again, the idea behind this one was what? We wanted to instead of worrying about taking a derivative, we looked at the secant line through 2 points, figured out where that secant line crossed the x-axis, threw away the farthest away a 1, brought in the next one, and kept going, right? That recursive process. Again, not looking for, obviously, since we're doing things by hand, not looking for long-winded processes here. Just do a few. These were our 3 root finding root finding methods that we had. Polynomial interpolation, we had a couple of methods for doing that, right? One was the Lagrange cardinal polynomials. Again, not looking for long-winded here. If you can do it for a quadratic, you can do it for any of them, right? The idea behind the Lagrange cardinal polynomials was create polynomials that are equal to, create polynomials that are equal to 1 when you plug in one of the values and 0 for the rest, and then multiply them by the appropriate function values. Again, we'll be looking to do that for a quadratic. So 3 points, find a quadratic root. Not looking for anything long. If you can do it for a quadratic, you can do it for anything, right? You can also knock over the table if you're not paying attention to where you're walking. All right, the other method we used was divided differences. Again, looking at mainly 3 steps. In this case, 3 steps will get you down to a cubic, right? Because you do your basically slopes first, and then you look at the next ones will be more slope ideas, except they're a little bit expanded, and then another slope idea at the end, and pick off the coefficients that you need. I'm not going to be looking for you to simplify any polynomials. What I mean by that is, as an example for the Lagrange cardinal ones, say you had something like the points -1, 8, 2, 11, 5, -6. Just making up numbers as I go along here. If you want to find your polynomial, well, again, I want to create 1 when I plug in -1 and get 8 out, right? So I would do x minus 2, x minus 5. That makes it 0 for the other 2. I want to make it 1 when I plug in -1, right? That's how we create that first term. Leave it. Don't simplify. That's what I'm saying for that. Okay. So your next one would be what? Yeah. And I really don't care if you simplify it. You can just leave it like that. Last one. Good. Yep. And just leave it. That's fine. That would be a whole problem. The end. Okay. Same with the divided differences. If you started off with, I'm going to make up some points, so the numbers could get ugly to start with, but let's make it a little bit easier. Let's say we had 1, 2, 2, 5, 3, 1, 4, 7. And I want to find the cubic. All right, so those are your x's and your f of x's, right? What do we do first? Yeah, difference of 5 minus 2 over the 2 minus 1. So we get 3, right? 1 minus 5 over 3 minus 2 gives me negative 4. 7 minus 1 over 4 minus 3 gives me 6. And that would be your, the way the book labels it is like that, right? We do the same thing for the next one. Negative 4 minus 3 over what? Yeah, the 3 minus the 1, right? The farther one's away. So you get, what is that, negative 7 halves. 6 minus a minus 4 over what? 4 minus the 2. So we get 5. And then finally, so we would have, what'd you say? So that's 10, 17 over 2 over 3 is 17 over 6. Is that what you said? Yeah, good. Yeah, good. Nice. Everybody okay with making the table? Right? Now we got to pick out the information for what we need, right? What do we look at in the table? Yeah, this part here, right? Okay, so how do we create the polynomial then? Yeah.
Minus 7 minus, minus 1 minus 2.
Good.
Plus 17 minus 6. Minus 1 minus 2 minus 3.
Good. So remember that I want 2 to come out when we plug in 1, right? So in the last 3 terms, I better have an x minus 1 piece if I'm going to use 2 to start it. Right? We created this 3 based on the fact that I wanted to get 5 out when I plugged in 2. I don't want to change it when I do the next one, so I want x minus 2 on the next 2, and then finally an x minus 3 on the last one. Are we okay with creating that polynomial? Again, cubic is what I would expect it to do. Okay? All right. Then the last thing we've been talking about is your Richardson extrapolation. Estimate an approximation, probably going to be a derivative because that's what we've been estimating most of the time, right? So estimate a derivative using the extrapolation process. Just like what we did in the example at the beginning of class, right? Same idea. Remember that you're guided by that is getting the next ones, right? Rather than using a bunch of symbols, that's what you're guided by, correct? What goes in here is the order at that step, right? So if you start with an order 1 approximation, your new first column will be you put a 1 in for the exponent. Your next column will be a 2. And you put in for the exponent, the next column would be a 3 for the exponent. Okay. When we did the central difference one, remember that was an order 2 approximation, and we know that we eliminated all the odd terms, right? We did a 2 the first time, the next one was a 4, the next one was a 6. Depends on what the order of the approximation is that you know. But make sure you can carry out a few steps of that as well by hand with a calculator. Again, calculator active, but I don't want to make it onerous, right? Okay? Be something that should be relatively straightforward to calculate. The only thing you really have to keep track of here is, if you remember the formula, is what your constant needs to be in front that you're going to multiply by. And the last thing is to, like what we talked about, I'm not sure create's the right word, but I'm going to use create an approximation of a given order based on function values. I will give you the function values I want you to use and the order that I want you to get. Okay, so you won't be guessing, right? It'll be like those last two problems that we did. Questions on anything that I'm expecting you to do? Shouldn't be hard to guess. Okay? Right? Shouldn't be hard to guess at all. We had 3 different types of things that we've done so far this semester. Do those 3 different types of things that are on your exam. Any questions at all related to the exam? Yeah, Max.
Nothing to do with R.
Nothing to do with R. No, that'll be in your major assignment. That'll be outside of class. So yes, you will have something to do with R, but that's not on the exam. Other questions at all? I really don't want you to have to code on the fly. Yeah. Yep, you're welcome. All right. Well, that's enough for today then. Holler at me if you've got questions. But again, like I said, should not be hard to guess what kind of problems I'm going to ask you. I think I was fairly explicit. I'm going to completely blindside you with something that you haven't seen before. Exactly. That sounds like me.